Have you ever really stopped to think about how the complex machines we use every single day, our cars, the airplanes we fly in, even the bridges we drive over, don't just fall apart? Well, it's not some kind of magic. It's a field called machine design, and it's this hidden world of engineering that makes sure the things we build actually work and last. And today, we're going to pull back that curtain. I mean, just look at this jet engine for a second. When a plane is taking off, the forces trying to tear those fan blades to pieces are just astronomical. And yet, they hold together, flight after flight. So how in the world is that possible? How do you even begin to design something to survive that kind of punishment? Well, it turns out engineers have a kind of secret language for these problems. It's a language built on physics and material science. And you know what? By the time we're done here, you're going to understand the basics of it too. You'll start to see the world in a whole new way, through the eyes of a designer. So, what is machine design really? At its heart, it's the art and science of creating all the individual parts that make up a machine. And the goal sounds simple, but it's incredibly tough. Make things that do their job reliably, safely, and for a very, very long time. So where does an engineer even start? Well, it almost always begins with one thing, the materials. Because you could have the most genius design in history, but if you make it out of the wrong stuff, it is absolutely guaranteed to fail. And that's really the whole ball game right there. You see, understanding materials isn't just some nice-to-have skill for an engineer. It is completely fundamental. It's the bedrock that every single other decision is built on. And when you look at these properties, you really start to see the balancing act that engineers have to do. They're not just looking for the quote-unquote strongest material. They have to ask, does it need to be strong but also kind of flexible, like a car spring? Does it need to resist rust? How easily can we shape it? All of these things have to be weighed against each other. This table just proves the point perfectly. I mean, look at this. All of these are technically steel, but just by adding tiny amounts of other elements, a little chromium for gears, some silicone for springs, their properties just change completely. Each one becomes a specialized tool, tailor-made for a very specific job. Okay, so you've picked your material. Now you've got to understand how it's going to behave when you put it under pressure. This is where we get into the real physics of it all, the stuff that separates a great design from a total disaster. First up, we have to talk about load, and it's really simple. A load is just any external force that a part has to deal with. It could be the weight of a truck on an axle, the pressure inside a pipe, or the tension on a crane's cable. It's the outside world pushing or pulling on your design. Now here's where it gets interesting. When you apply that load, the material doesn't just passively take it. On the inside, its molecules are literally fighting back. And that internal resistance, that fight, is what we call stress. Think of it as the material's internal grit, its will to not get pulled apart. So what happens as a result of that internal battle? Well, you get strain. Strain is the physical change you can actually see and measure. It's how much the part stretches or bends or gets compressed. So if stress is the invisible internal fight, strain is the visible outcome of that fight. Now, this might sound completely obvious, but it's probably the single most important rule in all of engineering. You never, ever design a part to handle exactly the load you expect it to. You always build in a safety margin. You have to design it to be stronger than it needs to be. Which, of course, brings up the million-dollar question, doesn't it? If you're building in a safety margin, how big should it be? Should the part be twice as strong as it needs to be? 10 times stronger? How do you decide? Well, for a whole lot of everyday things, this is the sweet spot, somewhere between 2 and 4 times stronger. We call this the factor of safety, and it's basically an engineering safety net. Why so much? Well, it accounts for things you can't predict, like sudden impacts, tiny flaws in the metal you can't see, or just plain old wear and tear over decades. It's the reason a chair doesn't snap when you drop into it a little too hard. So, to put it in official terms, the factor of safety is just a ratio. It's the maximum stress the material could handle before it breaks, divided by the stress you're actually going to let it experience in the real world. It is probably the most critical tool an engineer has to make sure things don't fail. Okay, so we've picked our materials, we've calculated our stresses, but here's the thing, machines are almost never made from a single solid piece of metal. They're collections of many parts. So, how do you connect them all together in a way that's just as strong as the parts themselves? Generally speaking, you've got 2 main approaches. You can create a permanent bond, like with welding. It's super strong, but it also means you can't really take it apart for repairs. Or you can go with non-permanent fasteners like nuts and bolts, which let you do maintenance. The choice you make really depends on what the machine is for. And you can see the two ideas right here. On one side, you've got welding, where you're basically melting two pieces of metal so they become one solid piece. And on the other, a simple nut and bolt, which gives you an incredible amount of clamping force, but you can always unscrew it. They are two very different answers to two very different problems. All right, let's zoom out for a minute. We've talked about the ingredients, materials, forces, fasteners, but how do engineers actually put all of this together? What's the playbook for going from an idea on a napkin to a real-world machine? Well, they follow a process. It's a logical, step-by-step method that starts with a problem and hopefully ends with a great solution. But notice that last step, analyze and refine. This isn't a straight line. It's a loop. You test, you learn, and you go right back to the drawing board to make the design better. And this is just so important to understand. Great engineering is rarely about getting it perfect on the first try. It's an endless cycle of building, testing, breaking, learning from the failure, and then refining. That prototype is where theory crashes into reality, and that's where you learn the most valuable lessons. And looking at a car engine really brings it all home. You're not just looking at one single machine here. You're looking at thousands of tiny, individual design problems that have all been solved. Every single part, right down to the smallest screw, had its materials carefully chosen, its stresses calculated, its factor of safety applied, and its design tested over and over again. So the next time you sit down in a chair, open a door, or drive your car, just take a second to look a little closer. Think about the materials, think about the forces at play, and that hidden safety factor that's keeping it all together. Now that you speak a little of the language, what invisible engineering will you notice today?